Okay, so let's talk about a couple things. What I have here is a voltmeter. Now, there's a bunch of different settings here. Let's take a look at all the different settings. Off, that's obvious. Curly V, this is for an alternating current. See how there's a curly symbol above the V. V with a straight line across it, that's for direct current. So a little bit alternating current is when the current is going back and forth across the wire. It ends up, it's a lot easier to transmit power that way. We'll talk about why that is later. For now, just know, that's how those circuits work in your house. You probably know. If we look at an outlet, there's one right there, but I won't point it out. You've seen outlets before. The current is going, or the voltage is going back and forth. It's 120 volts this way, 120 volts the other way, and it oscillates. That's an alternating current. But this, we're going to stick mostly for now with direct current, which is this symbol right here. And then this is millivolts, so for smaller voltages. We'll talk about these other things later. But let's take a look at this battery. We're gonna wait. There we go. There's a battery, and it says right there 1.5 volts. So what I'm going to do is this thing here has 2 ports, and we can connect these 2 leads into here and then read what happens. Ooh, how can I do this while keeping it on display? So I'm gonna put one end right here. It's touching that metal part, and I'm gonna cover it up just so that, just know it's being touched by in there like that. And then if I put this side right here, hey, check it out. That thing says 1.476 volts. Right, so this is how we read voltages across a battery or any circuit here. Now what happens if I switch things? It was blue up, now it's blue down. Negative 1.5 volts, right? That makes sense because the voltage drop kind of has a direction. It's positive 1.5 volts this way, or if I reverse it, negative 1.5 volts in the other direction here. Cool. So that's just a little bit about reading voltage. Let's see what the voltage is of me. Oh, 0.053 volts-ish. If we put it to millivolts, I get some voltage there. Interesting. Okay. Might have to do just with like static electricity in the air. Now, let's go to our example. Here we go. A 4-volt battery, like this, but this is 1.5, is connected across a 10-meter wire, and it creates an electron current. Somehow we were able to measure that, of 4.1 times 10 to the 17 electrons per second in a 12-gauge copper wire. So very similar to, I don't have those exact things, but here's the idea. You have a wire, I attach it on this side, I attach it on this side, and you can't see it, but electrons are traveling through this wire when I make a closed loop here. Cool. And what we want to do is, under those specifics, calculate the drift velocity and tau, that mean time between electron collisions here. Oh, but the first thing I did, I wrote it out. Notice that electric field is delta V over delta X. In our case, delta V is 4 volts. It's a 4-volt battery, so it'll be 4 volts up as it goes through the battery, and then a drop of 4 volts through the wire. So that delta V is 4 volts over 10 meters, which tells us the electric field on average is 0.4 volts per meter in that wire. And we need that because taking a look at some of our formulas from before, we saw this one. Electron current is that electron density times area times the drift velocity. Well, we know that electron current, we were told it in the problem. Area we can find, I think I did here the calculation. It's a circular wire, pi r squared. 12 gauge wire has that 1.6 millimeter diameter, so I put 0.815 millimeters, half of that. And we got the areas the same as before, 2.1 times 10 to the minus 6 meters squared. And since it was copper wire, we look up or remember from last time that the free electron density is that number there. We were told the electron current, so we can just plug those values in for the drift velocity. I guess let's just try that real quick. The drift velocity, this is similar to before, would just be 4.1 E17 divided by 8.5 E28, oops, 8.5, not 5.8 times 2.1 E negative 6, and we got 2.2 times 10 to the minus 6 meters per second. I'll just leave it as that. VD equals maybe 2.3. Right, that's our drift velocity here. Now, the mean time between collisions, remember from before we had that formula, drift velocity is F over m times delta t. But F was E times E. So what we need to do, we're solving for that delta t or that tau, a little bit of algebra here. But oh look, drift velocity, that's kind of maybe why we did that here. Mass, that will be the mass of the electron, charge of the electron, and then E, which is the electric field in there, is that 0.4 volts per meter. So let's just write down our stuff. M is 9.11 times 10 to the minus 31 kilograms. E is the 1.6 times 10 to the minus 19 coulombs. We got the other values from before, and so that tells us the mean time between collisions. Kind of an interesting thing to know. Let's find out. 9.11 divided by, was it 0.4 times very small amount of time. The mean time between collisions, between an electron and something inside, an atom inside that wire, is going to be 3.2 times 10 to the minus 17 seconds, right? So very short, 3.3 if I round correctly. So they're not taking very long to collide with each other. Cool. Okay, let's take a short break.